Next, we will see the complement of a function. The complement representation for a function f or f prime is obtained from an interchanging of ones to zeros and zeros to ones for the values of f in the truth table. In general, if we have a variable x, the complement of x is x prime. So when x equal to 0, x prime will be 1. When x equal to 1, x prime will be 0. Now for any function f, the value of the variables for which we will get this f function equal to 1, then the complement of f prime will give us 1 for the values for which we used to get f equal to 0. Now the complement of a function can be derived algebraically by applying De Morgan's theorem. Let us see an example. Suppose we have a function f1 which is x prime y z prime plus x prime y prime z. Now if you are asked to find the complement of this function f1, so we can write f1 prime equal to x prime y z prime plus x prime y prime z whole prime. Now let us apply De Morgan's theorem. Consider this is one variable a and this is another variable b. So a plus b whole prime will lead us. Let's consider this is a and this is b. So using De Morgan's theorem, we can write a plus b whole prime, which is equal to a prime into b prime. So we can write x prime y z prime whole prime into x prime y prime z prime whole prime. Now if we apply De Morgan's theorem again here, then as they are multiplied, so we can write x prime prime plus y prime plus z prime prime. So this is one set and another set x prime prime plus y prime prime plus z prime. Here the prime will not be there. So this is the case. Prime will cancel out. So you will have x plus y prime plus z and x plus y plus z prime. This is the complement of function f1 in POS form. If you want to present it in SOP form, then you can multiply x plus x y plus x z prime plus y prime will give you 0. So x y prime plus z prime y prime plus xz plus zy zz prime will give you 0. So this is the function in SOP form. Now you can simplify this function by taking x common from here and you can do it by yourself. But this is the representation of f1 prime in SOP form. Okay, let me do the simplification. Take x common from here, 1 plus y plus z prime plus y prime plus z plus zy prime y prime plus zy. Now 1 plus any variable will return you 1. Finally, we'll get, if we go from here, x plus zy plus z prime y prime. So this is the simplified version. Let us see another example. Suppose f2 is equal to x y prime z prime plus yz. Now if we apply De Morgan's theorem, then f2 prime will be equal to x y prime z prime plus yz whole prime. Now first of all, let's apply in this fashion that this is a and this is b. We can write x prime plus y prime z prime plus yz whole prime. From here we can write, if we apply De Morgan's theorem again, then x prime plus y prime z prime whole prime into yz whole prime. This will return us x prime plus if we apply De Morgan's theorem on each portion, y prime, z prime, and yz portion, then we'll get prime prime will cancel it, so y plus z into y prime plus z prime. So this is the complement function of f2. Now let me show you complementing a function by using duals. See the procedure. Let's solve for f1. Suppose we have a function f1 which is equal to x prime y z prime plus x prime y prime z, the same function we are taking. First of all, what you need to do, you need to take the dual of this function. So if you take the dual of f1, that will give you x prime plus y plus z prime. All the AND will be converted to OR, and all the ORs will be converted to AND. So this OR will be converted to AND, and here we'll get x prime plus y prime plus z. Now, in order to get the complement of function f1, what you need to do, you need to take the complement of each literals or each variables. So if you take the complement of each variable, then that will give you f1 prime. So if I take the complement of this x prime, we'll get x plus y prime plus z. Here x plus y plus z prime. This is the complement of function f1, which is equal to this portion. I hope this method is quite easier. You can find the complement of this function by taking dual by yourself. You will get the same result that we obtained here. Let me tell you the procedure again. First of all, you take the dual of the original function and take the complement of each variable. That will give you the complement of that function. That's all. Now we will see AND or implementation of an SOP expression. Suppose we have a function f equal to ab plus c into d plus e. Now this is neither SOP nor POS. We can implement this function using logic gates at its current form, or we can convert this function to SOP form. In order to convert this function to SOP form, what we can do, we can multiply c with d plus e. Let's do it. In SOP form, this function becomes ab plus cd plus ce. Now let me show you the logic gate implementation for the both functions, though they are same functions but represented in different way. First of all, this one, a b, they are ANDed. Then we have c, that is multiplied with d, and d and e are ORed, and this will be ANDed with c. Finally, this output will be ORed and we'll get f. Now if we implement the second function, a b c d c e, a b ANDed, c d ANDed, c e ANDed, all the outputs will be ORed together and we'll get f. Now, what are the difference between these two sets of implementation? First of all, here we are having 3-level circuit implementation. How? This is one level. This is level 1. Level means whenever we'll give the input, each gate requires a certain amount of time to provide the output. Suppose each gate is taking 1 nanosecond, 1 nanosecond, 1 nanosecond for providing output. Now, in first level or after first 1 nanosecond, we'll get this output and this output ready. Unless we get D plus E, even though C input is available, the output that is available here will not be correct because D plus E is not available here. So once D plus E is available, it will go for second level implementation. This is level 2. And finally, this is level 3. So you can see in first level, that means after first 1 nanosecond, these outputs will be available. Then second 1 nanosecond, this output will be available. That means after 2 nanosecond, we are getting the output here. Then after 3 nanosecond, we will get the final output. But in SOP expression, suppose each gates are taking 1 nanosecond to provide the output. So this is level 1, and this is level 2. So after 1 nanosecond, all these outputs will be available, and after second 1 nanosecond, the function output will be available. So after 2 nanosecond, we'll get the output. So this is AND or implementation of an SOP expression. All the SOP expressions can be implemented using and OR gates having two-level implementation. This is the advantage of SOP or POS expressions. I'm going to show you the POS case as well. Now, before I go for the POS case, let's see the NAND-NAND implementation. NAND-NAND implementation of SOP expression. SOP expression. Using the De Morgan's theorem, we know AB whole prime can be written as A prime plus B prime. Now, if we have a function like this, AB whole prime, this bubble will make it whole prime. So this is AB whole prime. This can be written in this format. AB, first of all, they will be primed and then OR. So we can put bubble here. These two gates are giving the same type of output. Here A is inverted first, that will give you A prime. B is inverted first, that will give you B prime, and then they will be ORed. Eventually you will get A prime plus B prime. According to the De Morgan's law, this gate can be written in this fashion, NAND gate, or this NAND gate can be written in this fashion. The inputs will be inverted first, then they will be ORed. Now let's see this example. Suppose we have F equal to AB plus CD plus CE. We can implement this function using AND OR implementation having two-level gates, A, B, C, D, C, E. This is the two-level implementation. We already did it here. Now, if we put a bubble here and put a bubble here, this invert and invert will be cancelled out. So there is no problem if we put double invert to any line. That will not cause any change in the output. Again, if we put a bubble here, that will invert the output. Again, if we put a bubble here, then again the output will be inverted, so we'll retain the original output. So there will be no change in the result. Again, if we put a bubble here and put a bubble here, there will be no change. Now this gate where the inputs are inverted first, then they are ORed, this can be converted to NAND gate from this expression. So we can write this circuit implementation can be written in this fashion: A, B, C, D, C, E. We have NAND gate here. We have NAND gate here. We have NAND gate here. All the outputs will be NAND again, and we'll get the final function output. So this is two-level NAND gate implementation of a SOP expression. This is level 1 and this is level 2. Level 1, level 2. This representation also sometimes named as two level NAND implementation. Now, if you are asked to represent any function having two-level NAND implementation, what you need to do? Represent the function in SOP form, then provide each product term through first level NAND gates, then all the outputs will be sent through second level NAND gate, and you'll get the final function output. The method is very simple, but we have learned how the theory works. Next, we'll see OR and implementation of POS expression. Suppose we have a function f equal to a plus b, b plus c plus d into a plus c. This is product of sum form. Now let's implement this a, b, then the second part is b, c, d, and the third part is a, c. So a or b, b or c or d, they will be ORed together, a or c. All the outputs will be ANDed and we'll get the function output. This is also two-level implementation. This is level 1 and this is level 2. Level 1, level 2. In level 1 we have OR gates. In level 2 we have 1 3 input AND gate. This is also called two-level implementation of POS expression. Now let's see NOR implementation. POS expression. Again, from De Morgan's theorem, we know a plus b whole prime can be written in this fashion, a prime into b prime. Using the gate implementation, we can write a plus b, and this bubble will give us whole prime. This is a plus b whole prime. This gate and the gate here, we have a here, b here. First of all, they will be not a prime, b prime, and they will be ANDed. We will get a prime, b prime here. They are having equivalent output. So let's see this function. F equal to a plus b, b plus c plus d, a plus c. So we can write a, b, b, c, d, a, c. All these three will be ORed. This is first level using OR gates. And they will be ANDed together. Now, like the previous case, if we put two bubbles here, there will be no change in the outputs. So we can place two bubbles in same line. We are getting f here. If we consider that here the inputs are x, y, z, we can write the function output f equal to x prime, y prime, z prime. They are ANDed. And using De Morgan's theorem, this can be represented in this fashion, x plus y plus z whole prime. So they will be ORed together, then the output will be inverted. So we can write a, b, b, c, d, a, c. We have one OR gate here, not OR gate, NOR gate, b, c, d, another NOR gate, a, c, another NOR gate. Now this inverted AND gate can be represented as NOR gate from this equation. So this is two-level NOR gate implementation of POS expression. It is also named as two-level NOR implementation. Now, if you are asked to implement any function using two-level NOR gates, what you need to do, express the function in POS form. Then each sum term should be sent through the first level NOR gate. Then all the outputs will be sent through the second level NOR gate. You will get the function output. And the theory is clear from this concept. Next, we'll see NAND gate and NOR gate as universal gates. A universal gate is a gate which can implement any Boolean function without need to use any other gate type. Using NAND gates and NOR gates separately, we can implement the basic gates. That means AND gate, OR gate, and NOT gate. In practice, this is advantageous since NAND and NOR gates are economical and easier to fabricate. Let us see implementation of NOT gate, OR gate, AND gate. Let us see the implementation of NOT gate using NAND gate first. This is NAND gate. There are two inputs. They will be shorted and input will be given here. The function output f will be a prime. This can be easily derived. A multiplied with a will give us a, and once it goes out due to this bubble, we'll get a prime. Now the OR gate implementation using NAND gate. For two input OR gate, we have a and b. A should be passed through one NOT gate. That means the NOT gate implemented by NAND gate. They must be passed through another NAND gate. Here we'll get a prime, b prime. Here we'll get a prime into b prime whole prime, from which we can get a plus b by using De Morgan's theorem, which is equivalent to OR gate. We give a, b input, we'll get a plus b as output. We are giving a, b input and we are getting a plus b as output. This is the OR operation, and this OR gate is implemented by using NAND gates. The AND gate implementation using NAND gate, a, b, we'll get a, b whole prime. Again, if we pass it through another NOT gate, we'll get a, b. So these are the implementation of NOT gate, OR gate, AND gate using NAND gate. Next, we'll see the NOR gate implementation of the basic gates. First of all, NOT gate. The NOT gate can be implemented having similar pattern that we did for NAND gate. If we have a input, a or a will give us a, and here due to this bubble we'll get function output a prime. So this is the NOT gate implementation. Now the OR gate implementation. For two input OR gate, a and b, they will be ORed, and due to this bubble we'll get a or b whole prime. If it is sent through another NOT gate, which is implemented by NOR gate, we'll get a or b. This is the equivalent circuit of OR gate. Now the AND gate implementation, a, b. First of all, a will be inverted, b will be inverted. The outputs will be sent through another NOR gate. Here we'll get a prime, here we'll get b prime, and here we'll get a prime or b prime whole prime. Now using De Morgan's theorem, this can be written as a dot b. So this is the equivalent circuit of AND gate. We are giving a, b as input and we are getting ab, which is the ANDed output.